Swayam Prabha. Digital India. Educated India.
Welcome to Module 8, Lecture 3. In the last lecture, we just started, we just concluded. When we were concluding, we talked about the depassivation of rebar, and we just mentioned about the service life of simplest model for service life of concrete, reinforced concrete in the context of rebar corrosion. And we said that two phenomena which causes depassivation, one of them is carbonation, the other is chloride. So, we look into carbonation process, models, protection, chloride ingress, process, models and protection, right. So, just to recollect, the service life with respect to corrosion we defined like this in the last class. We just mentioned this diagram, same diagram we have looked into in the last class, where we said that initially concrete is reinforced concrete provides protection to the rebar, and with time this may get affected if it is exposed to a chloride environment, or if it is exposed to atmosphere where carbon dioxide from the atmosphere can come and reduce its pH. So, we also mentioned last class that pH of concrete at certain pH values or high pH values, actually the oxide forms passivates the steel, in other words forms a layer over the steel bar, which essentially do not impair with the performance of the reinforcement bar, and in fact, it protects it, and that is a passivation layer. So, it is essentially oxide coating, thin, thick, dense, thin but dense, through which Fe cannot go into the solution, and rate of formation of such oxide is very slow, and therefore, we may not term this as active corrosion. So, this is passive condition. Now, this passive condition is broken down during this period of time, and that is what we call as depassivation time, and this can occur either because of carbonation or because of free chloride. We will define free chloride later on. What is free chloride? Because there must be then, if it is not free chloride, there must be something else, bound chloride, total chloride, we will come to that later on. So, once the depassivation has occurred, that is the layer of oxide which is formed on top of the rebar at high pH level is destroyed at a pH value which is low. When pH turns out to be low or sufficient chloride has come, then corrosion process might start, and the time after which you have a serviceability limit is reached, which is actually time of appearance of first visible crack. So, the time at which first visible crack is observed, because corrosion process results in cracking, which we will see later on how it does. So, when first visible crack has appeared, that time we call as service life. That is, there is a limit of serviceability limit. When a first visible crack has appeared, this time we call as corrosion time, and total service life is of the element is T p plus T c. So, service life of the element is T p plus T c. So, today we will look largely into this phenomena, how it get depassivated. First we will look at carbonation, and then we will look at chloride. Carbonation process, if I look at it, you see carbon dioxide from the atmosphere penetrates into concrete from the surface as shown here, and it can, in presence of moisture, it can form carbon dioxide plus water can form carbonic acid, and this carbonic acid actually can react with, let us say, sodium hydroxide to form sodium carbonate plus water. So, sodium hydroxide, that is alkali, is present, or potassium hydroxide, they are present in the cement material, cementitious material, concrete system, and it can react forming sodium carbonate and water. Now, this sodium carbonate or potassium carbonate can react with calcium hydroxide in the cement, forming calcium carbonate and again water, and this also can form in this manner, it can form calcium carbonate and sodium hydroxide, calcium carbonate and sodium hydroxide, this should be sodium hydroxide and this should be 2 sodium hydroxide and this should be potassium hydroxide plus potassium hydroxide. In other words, calcium carbonate is formed, and if we write it straight away, simple reaction, calcium hydroxide plus carbon dioxide in presence of water actually would form calcium carbonate and water. Now, since calcium, the calcium hydroxide or sodium hydroxide material is getting consumed in the process, therefore, the pH of the concrete will reduce down. To start with, pH of the concrete is around 12 to 13. So, pH of concrete to start with is around 12 to 13, which can get reduced down to even lower value than 9. What we understand is the intermediate step is sodium hydroxide and potassium hydroxide. So, calcium hydroxide provides a kind of reserve alkalinity. Once sodium hydroxide and potassium hydroxide, they do not get consumed initially, they are just the in between steps. So, sodium hydroxide and potassium hydroxide, they react with carbonic acid, which is formed because of the carbon dioxide coming from the atmosphere in presence of moisture. This reaction can proceed and sodium carbonate can react with calcium hydroxide, forming calcium carbonate. In this process, calcium hydroxide, which is a sparingly soluble salt, will get dissolved more into the pore solution. Part of it was soluble, got dissolved, and part is still as precipitate. So, this precipitate will dissolve more and more as it is consumed from the system to form calcium carbonate. A time will come when even the sodium hydroxide and potassium hydroxide will all get consumed, because all alkaline material will get consumed by carbon dioxide. And under such situations, when all alkaline materials including sodium hydroxide and potassium hydroxide has been consumed by carbon dioxide from the atmosphere in presence of moisture, forming carbonates, pH will reduce down significantly and pH will be less than 9 now. And when it is less than 9, depassivation can occur. Depassivation can occur at certain lower pHs, Fe3O4, the oxides may not be stable under such situation at low pH, and actually the black crust, which I talked about in the last class, may not be stable, and now red rust formation may occur, which occupies a lot more volume than the volume that is occupied by black rust or the steel, and thereby can cause expansive pressure. We will come to that sometime later on. Now, therefore, what we see is pH can get reduced down by consumption of the alkaline material. Intermediate steps are not given here, but I just discussed them. But how do the carbon dioxide penetrate? It penetrates through the pore in the system, and as it penetrates, and it must be moist pore, the pore must be also moist, there must be moisture here. If there is no, in absence of moisture, reaction will not proceed, because it occurs in solution phase, carbonic acid will not form. So, carbon dioxide plus water is necessary, and therefore, water has to be there. So, it comes through the pores, water has to be there, and as all alkaline material up to this zone is finished, we call it the carbonation, carbonation reaction has occurred, and it has carbonation, carbonation neutralization. So, this is the neutralization depth, and that is the carbonation depth. So, we call it carbonation depth, we call it carbonation depth. So, up to which carbonation depth, up to which all the alkaline material has got neutralized by carbon dioxide coming from outside. So, again the pores are important, moisture situation is important. Now, if it is a fully submerged concrete, moisture will be available, but carbon dioxide concentration will be very low in dissolved water. And if it is a fully dry concrete, reaction will not proceed, all the carbon dioxide is there. So, this occurs only at a certain relative humidity. Now, if you remember, when we talked of carbonation shrinkage, around 55% relative humidity carbonation was carbonation shrinkage was maximum. In other words, carbonation proceeds maximum at carbonation is maximum at 50, let us say 50 to 60% RH. So, 50 to 60% RH carbonation is maximum, 100% RH it reduces down, and if it is fully moist, actually no carbonation will occur. To have carbonation or for carbonation to proceed, I need both oxygen or both carbon dioxide, that is air is present in air, about 3% or so depending upon the situation, and of course, the moisture. So, that is the carbonation process, that is actually the carbonation process, that is the carbonation process. Now, we can what is of our interest is the carbonation depth. If I call x as the carbonation depth, this is important for us, carbonation depth is important for us, right, and we do model this carbonation depth, because when the carbonation depth reaches the reinforcement level, that is the time depossivation can occur. So, therefore, service life with respect to carbonation will be defined when carbonation depth has reached the river level or more. All right. Now, how does carbon dioxide comes? See, there is a concentration of the carbon dioxide, concentration of the carbon dioxide is low in the concrete, outside it is more. To start with concentration. So, it is basically molecular diffusion. Molecules are in Brownian movement. So, outside carbon dioxide molecules, they will be in Brownian movement, and they collide with each other as long as concentrations are same. But where concentration are less, carbon dioxide molecule will not be able to interact with the same molecule. So, what will happen? They will penetrate inside, they will jump. So, you have, if you have high carbon dioxide concentration here, let us say high carbon dioxide concentration, and less carbon dioxide concentration here, low carbon dioxide, low CO2, high CO2 high, the molecule will move along this direction, and since they will not be able to interaction, less molecule will be available for interaction here or collision, more molecule will tend to move. So, they will try to diffuse. So, this is molecular diffusion, right. So, basically in liquid situation, of course, it is a concentration difference. So, concentration difference is the driving force, and we said in case of liquid, last class we mentioned that there could be osmotic pressure difference, and that could be the driving force behind such diffusion. So, carbon dioxide from outside tend to diffuse inside, and this diffusion process is governed by fixed diffusion law. Okay. So, fixed diffusion law says the flux, diffusion flux could be in some unit kg per meter square per unit time. Diffusion flux is proportional to dc dx, where c is the rate of c is the concentration gradient, c is dc dx is the concentration gradient, c is the concentration. So, in our case c is CO2 by dx, and the constant of proportionality I will call it carbon dioxide diffusion coefficient. So, flux q is proportional to dc concentration gradient of the carbon dioxide. So, carbon dioxide concentration here would be 0, here would be much higher, that is atmospheric carbon dioxide, and therefore, it will this is the x dc dx, if I am considering a small length dc dx. Let us say carbon dioxide concentration is high here, low there. So, one can think in terms of it is proportional to concentration gradient, concentration gradient. Now, this is what is fixed diffusion law, and if you are looking at the mass balance, then you will get actually rate of change of concentration with time. Rate of change of concentration with time will be given as d c x square. It is a diffusion equation, heat diffusion equation, quite a number of diffusion equation follows this. So, this is the second equation, but anyway we are not interested in this manner right now. We are not interested in this one right now. We are not interested in this one. We are only interested in this. So, the flux is proportional to concentration gradient. Flux is proportional to concentration gradient, right? Flux is proportional to concentration gradient. So, dq, if I consider the flux at this has already got up to x, it has got already carbonated, it has got the concrete has got carbonated up to x. So, concentration between C 0 outside, C 0 here and C in the concrete is here. So, concentration gradient will be given as C 0 minus C divided by x, that is concentration gradient. D is the diffusion coefficient, D is the diffusion coefficient, and if A is the area, flux is per unit area. So, quantity, the dq is the quantity of carbon dioxide coming to this dx element, right. So, there is no this is already carbonated, this is carbonated, already carbonated, like we shown in the last diagram, already carbonated up to x, depth x, and now the carbonation is occurring at dx element, carbonation is occurring over this dx element. So, as it comes in, the gradient will be C 0 minus C, where C 0 is outside, C C is the inside, divided by x, that is the gradient, and we assume that gradient is constant there, multiplied by the area A, and this is the amount of carbon dioxide that would be coming in, the flux that would coming into dx, multiplied by dt, that was the rate. So, quantity of carbon dioxide coming in. So, dq stand for quantity of carbon dioxide in is d C 0 C C divided by, so d A C 0 minus multiplied by dt. So, that is the quantity. I should have used J for flux, J is equals to d del C del x, somebody could have written it like this, J is the flux. This is the quantity, this I am talking of quantity. Now, this if it is getting all neutralized at this moment, it is getting all neutralized at this moment. Let us say A is the alkaline material present, small a is the alkaline material present, alkaline material that is being neutralized, let us say it is all. So, the total volume of carbon dioxide coming, total volume of or total mass of carbon dioxide coming, that will dissolve, that will actually react with the alkaline material present in the dx. So, dx into A is the volume, dx into A is the volume, dV volume, and total carbon dioxide consumed. Let us say A is the alkaline carbon dioxide consumed by alkaline material. A is the carbon dioxide consumed by alkaline material, which I can find out from stoichiometry if I know the total alkaline material present per unit volume, right, and multiplied by the stoichiometric factor. So, A is the carbon dioxide consumed by the alkaline material present in dx. So, A dV, A is the carbon dioxide consumed per unit volume in the dx element. So, A into dV, that is A into A dx, that is this must be equals to dq. So, dq is the quantity that comes in dt time, and it is all consumed, right. So, for the alkaline material present multiplied by the stoichiometric factor, that will give you the carbon dioxide that can be consumed. So, A is the carbon dioxide that can be consumed by the alkaline material present, small a is the lowercase a is the amount of carbon dioxide that can be consumed by the alkaline material present in unit volume of the concrete. So, A is the carbon dioxide consumed by alkaline material present in concrete per unit volume of concrete. So, then A dV or A small a dx must be the equal to dq. So, that is the idea. So, it must be equals to dq. So, if it is equals to dq, then I simply integrate this some constant, that is 1 by x into some constant, let me call it k dash dt is equals to some other constant, that is a k double dash dx. So, what I will get if I will get k, if I integrate dt and this side it will be some constant, let us say k 3 prime x dx, integrate it. So, I will get it x square by 2. So, in other words, k, all this can be k, all this can be put, so I can write that t is equals to some constant, t is equals to some constant, let me call it at k 4 prime into x square. So, in other words, I write x equals to k under root t, that is what I have done. So, by simple integration I can find out x equals to k under root t. Now, this model is very simple model, absolutely simplistic, assuming the properties of this is all uniform after even carbonation, and it is not considering many factors, actually it does not consider many factors. But one thing comes out from this expression is that x is proportional to root t, x is proportional to root t. So, this is very simple model, and actually x is proportional to root t is what is comes out from this kind of a model, all right. But there are complex models, but there finally most of the model makes it some form of t to the power half relationship, because experimentally also this is largely been found to be valid. So, k is the question. Now, k depends upon many factors. This is for our qualitative understanding. One thing, the depth of carbonation at any time is proportional to root over t, the time from the starting of carbonation. That more or less fits in well with the experimental data. But constant of proportionality, empirically people have seen that it is a function of C environment, C air, A and B are two constant, and strength of the concrete. So, C environment and C air we have talked about. Now, Fm is equals to Fck plus 8. So, it is mean strength, actually one can take it that way, and A and B for different combinations of blended cement, blended cementitious material and OPC are given. For example, for Fm to the power B, it is for OPC A is 1800. So, that means K will be higher, but it is also B is minus 1.7. So, this is higher, but this minus 1.7 means the higher the strength, actually K would be lower, higher the strength K will be lower compared to, let us say, fly ash, silica fume or blast furnace slag blends. Normally blast furnace you can go up to 70%, silica fume people use about 9-10% and fly ash use 20%. So, this is a kind of practical blends which one would use, and these values are about empirical is suggested values are 1.2, minus 1.2, etc., etc. And if you calculate out this, let us say 1800 into some strength Fm to the power 1.7 minus, right, or in other words 1800 divided by Fm to the power 1.7, you will find this K value comes out to be low compared to 300 into divided by Fm to the power minus 1.2, I mean 1.2. See, this is nearly squaring up, and this is so if it is 50 MPa, this will be somewhere around 2000 or so, while if it is in this case 50 into 1 to the power 1.2 would make it 100 or so, let us say even I mean it is not even, it is just slightly more than 1. So, one can find out what is this value, but 300 divided by, it will be 3, this will be much less, this might be much less. So, blended this ones actually increases fly ash, silica fume, and this actually increases the K value somewhat. So, that means carbonation is likely to be faster for identical conditions of environment and air with blended system, with fly ash blending. Well, we have understood, because we know that the alkaline materials are consumed by this. Alkaline materials are consumed by blast furnace slag, silica fume. So, less alkalines, A will be now smaller A in the previous equation. A stands for, I mean A is the alkaline material or carbon dioxide required to consume, carbon dioxide required to consume alkaline material will be less. So, therefore, this these values should come like it comes appears like this. These values are, but that is nothing to worry much actually, because although the carbonation process must be faster, moisture ingress may be slower in this material, and also their microstructure is improved. Then their resistivity is high for this kind of material. Whenever you add pozzolanic material, resistivity increases significantly, as we shall see later on, and therefore, actually they do not create much of a problem when it comes to kinetics of corrosion. So, they have a tendency to depassivate, but when it comes to kinetics they might even prove better. C environment is 1 or 0.5, and for air entrained concrete C air is 0.7, otherwise 1. Air entrained concrete is more porous. Environment will depend upon whether it is exposed, because this empirical formula has been developed in Europe. So, Europe, if you keep it outside, then it is partially moist, right. I mean inside it is partially moist, outside if it is continuously wet, the values could be lower. So, this is continuously wet scenario. Now, root T experimental validation has been shown by some people. For example, most of it seems to fit with the root T curve. This also seems to be fitting with root T curve. So, this is in artificial climate, 20 degrees centigrade and 65% relative humidity. So, 20 degrees centigrade, 65% RH this one is, and this one is outdoor condition. So, there is lot of moist condition is prevailing here, and this is completely out of door flat. This is of course over a roof. So, this is more outdoor, like exposed to rain, this is more exposed to rain. So, what it shows is that root to relationship after all is quite often followed. So, this relationship, although very simple, so depth varies with root time, that becomes a kind of understanding that we try to develop or we develop from this situation, right. Now, we already said the degradation reaction in concrete takes place in moist environment, and concrete is not under fully saturated condition in tropical climate. Exposed concretes are subjected to wetting and drying. Even in western situation, colder climates, higher latitude, is actually under wetting and drying situation. Hence, moisture ingress of concrete is necessary element in service life model. So, all models must look into this wetting and drying. And if you look at it, for example, let us say in the our kind of climatic condition, this is your reinforcement bar, and if it is critical moisture line, there is a critical moisture content above which actually it will start carbonation will start. Now, in this case it is fully saturated in the beginning, then it dries out, it is shown as if it is fully saturated, it dries out to conducive moisture. So, above this moisture content there will be no carbonation, critical moisture level. So, if it dries out So, this zone becomes now critical and carbonation proceeds. This zone becomes critical and carbonation proceeds here, Then the drying stops here, suddenly wetting occurs, which occurs at a very fast rate, and then it has become actually saturated, no carbonation will progress. So, carbonation will progress only within this envelope, and this process will be repeated, and you can see this in this diagram. This process will repeat. Now, after this no carbonation, there might be a drying period, this there might be wetting period, then this is all saturated situation, no carbonation occurs. It starts again when moisture content reduces below critical level, continues with the same kind of slope, same kind of relationship, and in steps it actually happens. So, if you have cycles of wetting and drying, right, then carbonation will also progress in steps. Carbonation will also progress in steps, right. Carbonation will progress in steps. This is when it was fully wet, if it was fully saturated, but if it was fully dry, then also similar situation will progress. The moisture front, but this will be more complex. For example, you have fully dry, then critical moisture level, increase in critical moisture level. Here it will be more than critical moisture level, and there will be a critical upper limit of critical moisture content, lower limit of critical moisture content, upper limit of critical moisture content. Carbonation will only progress in between when it is fully dry and getting saturated. So, only beyond certain moisture level, lower limit of critical moisture content, above this is dry, then moisture reaches a lower limit of critical moisture content, carbonation, and then as wetting is continuing, this would be upper limit of critical moisture, upper limit critical moisture. So, carbonation will progress only in between, and this is during wetting phase. Once it is wetted, wetting is over, drying starts, this will come back like this, and this will also follow like this. Is a longer, because drying takes much longer time. So, carbonation will follow only during the critical moisture situation. Modeling that is relatively difficult, and people have not done any modeling on those so far. So, this is but in the Indian tropical scenario it will be like that. Consider, let us say, situations of any part of, let us say composite monsoon climate of central and northern India. You have monsoon season of 2 months. So, during this time period wetting will continue, but after that drying starts, and before the monsoon season it was fully dry. So, during the monsoon season wetting would start and the concrete will become moist, and conducive, if the situation is conducive for the cover concrete, carbonation will progress, and winter comes, it becomes more dry. After monsoon season, August, September, it tends to be dry, it will possibly continue, and when it becomes fully dry, humidity becomes very low, again it will cease to, carbonation will cease. So, it will actually occur between some time from the month of during the monsoon period to the winter period. After that it will stop when it has become fully dry, and again start next year. So, you will have cycles of carbonation in exposed concrete in Indian scenario when it is exposed to rain. Of course, in any other condition it could be different, but you see other case, the modeling is simple when you have a situation of originally saturated, which could be in the condition of Europe, where it is mostly saturated, sometime it becomes dry, then it will again become saturated. Now, moisture diffusion or moisture movement, it can be expressed through what is called Richards equation, which you have not looked into here at the moment, and it is Richards equation, which can be written like this: d theta relative moisture content dt is equals to del dx of d, which is a function of theta, into d theta dx. So, let me write it like this, del, again let me write it clearly, like again let me just write it clearly again. It can be written like del theta dt, where theta is relative moisture content, del x of d, which is a function of theta, del theta del x. This is Richards equation, and through this actually you can solve and find out the moisture profile. However, it has been, if you look at observed at this diagram, 1 hour, 2 hour drying, 3 hour drying, 12 hour drying. Even drying could be somewhat related to this, however, the boundary condition will be different, only the capillary moisture flow will be like this. Vapor transmission equation is also similar, it can be also modeled in a similar manner. Whatever it is, this is how drying follows. Drying follows, and it can also be shown to be proportional to depth varies with root time. It can be shown in a simple manner like we have done earlier in a simple model. One can show depth varies with square root of time. Therefore, if this is my critical moisture line, before that it was all saturated. So, relative humidity is 56% and 65%, and this is wetting. Wetting is instantaneous, drying takes longer time. So, this could be the cycle of drying and wetting. So, drying and wetting, right, for a given concrete. Experimentally also somewhat this can be validated. So, then you will have actually the carbonation front will progress in this manner. In the first cycle, you see this one can approximate the drying and wetting, because wetting is more or less instantaneous, then again drying and wetting, then there is a small gap, drying and wetting, small gap, drying and wetting. So, this is the conducive moisture condition during which carbonation will progress. So, carbonation progresses here, but then it will not progress further till this point, again progress in this manner, stop here, progress in this manner, and it follows till it reaches the cover depth, which is the cover depth is here, this is your cover. So, it reaches the cover depth. Now, one can see that during the second cycle, the duration during which carbonation is occurring is smaller. In the third cycle, it is still smaller, fourth cycle it will be still smaller, fifth cycle it is smaller, and so on and so forth. Now, what is this time? This is the time required for drying of the already carbonated depth. So, this is the time required for drying of the already carbonated depth. This is the drying, this is wetting, drying, wetting. So, this is the time required. So, the carbonation front in the first cycle reaches here, then it remains constant, second cycle it reaches there, third cycle it reaches there, and so on and so forth. So, if you see in the fourth cycle, the carbonation will only start when the depth up to which fourth cycle carbonation has occurred, the drying must take place up to that depth. So, one can algebraically formulate a formula like this, where B is the constant, the moisture penetration depth, if I call it x dash, is B under root T, because we said moisture penetration is also proportional to under root T. So, B is the constant of proportionality. So, x j going from 1 to j minus 1, where this is x j, is the carbonation depth, progress of carbonation depth during jth cycle. So, sum up all the carbonation depth prior to jth cycle, B divided by this, because B is equal to, so we want to find out the T. So, T will be T would be x dash square, x dash by B square, x dash by B square, right. T would be x dash by B square. So, T would be x dash by B square. So, therefore, this square of this gives me B divided by, that gives me the time 1 over it gives me the time. So, total time required up to which drying this time must be subtracted from total drying time. Total drying time minus this time must be subtracted, this must be subtracted from drying time. I think it is 1 over that, it should be 1 over that, because time would be x divided by B, x divided by B, or if I write it other round, 1 by like B x dash is equals to root T, B x dash is equals to root T. So, then I will have T equals to B x square. No, this should be 1 over that, 1 over that. So, this should be 1 over that, 1 over B divided by this square. So, you can find out this time, and k under root that will give you k, because k is the constant of proportionality for carbonation. So, x j will be k 1 over this, and this process every cycle you can find out how much is the progress of carbonation time. So, actually let me write this out clearly. X j is equals to T d, where T d is the drying time, that is this period, which is constant for all wetting drying cycle, or the time, every cycle time during which moisture condition is conducive. So, T d. Now, if you look at x dash, that is the moisture penetration depth, B under root T. So, unit of B is actually distance or length divided by root over T, So, if I square it up, so x T would be x dash square by B square. So, B B square. So, what is unit of B is length root over T to the power half, root over length T to the power half. So, length per unit T to the power minus half. So, therefore, this would be this would be simply sigma x j going from 1 to j minus 1, or x I going from divided by B square, and whole of this thing should be under root multiplied by k. So, let me write it again clearly, write this one clearly again, let me write this one clearly again, let me write this clearly again. The x j at x j, this, let me erase this out actually and write clearly x j, that is the carbonation depth at any cycle, jth cycle will be given as k under root T d, where T d is the cycle time or effective duration in every cycle during which carbonation can occur, minus, or put it like this, minus sigma x I going from 1 to j minus 1 by B square. So, this would be the so next x j. So, x j is the carbonation depth, progressive carbonation depth in jth cycle, progressive carbonation depth in jth cycle, and this you can repeat and find out. So, this is how we find out, this is how we can actually model this. Well, but what is important for us to understand is actually what is important for us, and when it reaches the cover depth, service life has been reached. So, what is important for us to understand is that the carbonation progresses in steps, and it would depend upon wetting and drying cycle, right. This is a simple model, this is a model for a specific condition, actual condition should be modeled under wetting and drying. If you have a crack, carbonation can penetrate along this direction. If you have a crack, carbonation can penetrate along this direction. So, diffusion of carbon dioxide first into the crack and then inside. So, in a cracked concrete, carbonation front might reach in this manner, carbonation concrete front might reach in this manner. Okay. So, if you have rebar somewhere it is coming, then there is a problem. What is protection against carbonation? Moisture and air is necessary, water saturated concrete exhibits lower rate of corrosion. So, keep concrete out of moisture. Time when carbonation front reaches the river level, that is we have understood. An impervious surface concrete, lower water cement ratio, adequate cover depth, improved protection against carbonation. So, this is all about carbonation. Now, we can look into chloride. We have two types of, when we are measuring chloride, we have two types of chloride. For example, you take some concrete, grind it to powder and dissolve it in acid, you get acid soluble chloride. I mean, you actually dissolve it in HNO3, 6 normal HNO3, concentrated nitric acid, then you get acid soluble chloride. Dissolve it in distilled water and find out by silver nitrate test the quantity of chloride, that is water soluble chloride, that is water soluble chloride, that is water soluble chloride. So, we distinguish two types of chlorides in concrete, one is water soluble, another is acid soluble. Depassivation takes place when chloride level reaches a critical value at the rebar. This is sometimes called threshold chloride level, and it depends upon cement and steel types. It depends upon cement and steel types, and service life is defined with respect to above depassivation. Of course, internal chloride is the chloride coming from ingredients, and IS 456-2000 tells you that this internal chloride, which is acid soluble chloride, total chloride, should be less than 0.4 or 0.6 kg per meter cube for RCC, for pre-stressed concrete 0.4 kg per meter cube. So, this is total chloride is important for ingredients, because some of the acid soluble chloride may turn to be water soluble chloride in future. So, if you have sufficient chloride right in the beginning, the TP, depreciation time, could be even 0. So, it is important that keep the new concrete free of chloride or below the values that has been suggested in the code, 0.4 kg per meter cube or 0.6 kg per meter. Some of the total chloride remain physically and chemically bound. Some chloride with the cement, like C3A reacting with calcium chloride gives you chloroaluminate salts, and higher C3A therefore improves the chloride binding. So, this is a chemically combined chloride. These are called Friedel salt, right. So, chloroaluminate salts, they are Friedel salts, and C3A binds it. Some could be physically adsorbed and they are also immobile, not able to move, not water soluble. So, chemically bound chloride is not water soluble and they would not contribute to depreciation, but they can later on become soluble, there could be a problem. So, therefore, total chloride, when we are measuring with acid soluble chloride, that actually includes the bound chloride and free chloride both. So, free chloride, bound chloride, both are there, all right. Acid soluble chloride indicates total chloride and water soluble chloride indicates free chloride. So, total minus free chloride gives you the bound chloride. Total minus free chloride gives you bound chloride. Sources of chloride in concrete, well, if it is fresh concrete, it may come from ingredients called chloride contaminated aggregates, admixtures containing chloride, which is of course restricted these days. Mixing water, quite often groundwater contaminated with chloride if it is used in concrete, and that is the case in many of the North Indian scenario. And then in hardened concrete, of course, they can come from outside. De-icing salts, that is very common in Europe, developed northern countries, Europe or United States of America. Chloride salts were used as de-icing salts. Seawater or in marine structures, chloride can come, we have discussed this earlier, and soil and groundwater containing chloride salts. So, these are sources of chloride. So, these are called internal chloride, these are external chloride which will come through ingress. Chloride content at reinforcement level at which corrosion initiation takes place are called threshold chloride, but it will vary with the cement type, C3A content of cement, because cement type mix proportion, steel type, not all steel will get depassivated. For example, a corrosion resistant steel may not get depassivated easily. So, sources of chloride penetration, it will depend upon that also. So, all put together threshold chloride will vary from cement to cement, steel to steel. So, that it cannot be unique, it cannot be unique. And therefore, you find that various codes have different values. For example, IS 456 we said this for RCC only 0.6 kg per meter cube, ACI 220.20 by mass of cement acid soluble chloride, 318.15 by mass of cement water soluble chloride. So, this is acid soluble, this is water soluble, BS 8110.4% by mass of chloride, and this is for total chloride, and Australian standard 0.8 kg per meter cube of concrete acid soluble chloride. So, you see it varies, and also it must be varying because of the experience also, it varies with the cement type and steel type. One thing we must remember that carbonation as well as chloride is not a problem per se for concrete, except for of course carbonation shrinkage. It is actually problem of the reinforcement, because they initiate the reinforcement corrosion. So, for concrete they are not problem. Therefore, we should address actually reinforcement corrosion or some indicators of reinforcement corrosion, whether it is initiated or not, with respect to chloride as well as carbonation. Right. So, in saturated concrete, if the concrete is saturated, the concentration of chloride ion will be high here and it may not be there inside. Chloride may diffuse by fixed diffusion equation. And actually for charged particle, it is electrical potential Now, if there is a concentration gradient of the charged particles, then the potential will also, there will be a potential gradient also existing, and that would cause driving of the chloride, ions, chloride ions. So, that is what we looked into in saturated condition chloride ions actually in saturated condition, chloride ions in saturated condition chloride ions are penetrating. These are all chloride ions. So, as the chloride ion penetrates, this high chloride ion concentration, higher potential here, less chloride ion concentration, lower potential. So, chloride ion move because of the potential difference, and it also can be expressed in form of the fixed diffusion equation, same fixed diffusion equation we talked about, right. So, this is the flux here, and if you look at the mass balance, then it can be written like this. If dCl is a function of the if this can be simplified, if dCl is not a function of the chloride concentration, this can be taken out, or of the space, then it can be taken out. So, if it is not a function of space or the chloride concentration itself, it can taken out, and it will be a linear equation. So, this is what it is. Mass balance will show you this kind of an equation. This is the flux coming in, and rate of change of this flux is rate of flux, whatever chloride coming in must minus going out must go on increasing the concentration. That is the idea, conservation of mass. So, this is the flux, rate of change of flux with space, that must be equals to change in concentration of the chloride within that space. So, finally, this is the diffusion equation, this is the diffusion. D is the independent of x and concentration, and therefore, you can simply write this kind of an equation. You can simply write this kind of an equation, but this is only valid for saturated condition. This is only valid for saturated condition. Now, solution of fixed diffusion equation for a specific boundary condition is available, but it can be solved today with finite element and so many types of tools available. It is not really difficult to solve. So, you can solve it, and since you can solve it, therefore, it is not very difficult to use this, but most commonly people have adopted to a specific solution for a specific boundary condition. For example, for a specific boundary condition of sudden change of surface chloride for a thick wall, this is available for heat transfer situation. For example, this is the boundary condition for infinitely thick wall, a semi infinite medium where T less than 0 concentration was C 0 everywhere, and T greater than 0 at x equals to 0, this is your system. At x equals to 0, this is semi infinite medium, this is infinity. At x equals to 0, suddenly you have changed the chloride's concentration to C s. Well, other side it has still remained same C 0, it was not changed. The solution is given by error function solution. Solution is given by this is the condition. At x equals to infinity, it is always C 0. Here x equals to 0, it suddenly changed to C s. For this solution is available, and this is given by C x t. At any point, the chloride concentration is given as C s, where C s is the surface concentration, which is kept constant, plus C 0 minus C s. C 0 is initial concentration, and at x equals to infinity, it still remains same, minus C s into error function, Gauss's error function of x by 2 d, where d is the diffusion coefficient and t is time, where error function of any y is any variable is given by this equation. So, this is a known solution, but this is not valid for all situations, although apparently a lot of people use this for all kind of situation. It is only valid for saturated chloride, saturated condition, that means possibly where no splash zone, submerged concrete, concentration outside is constant, tranquil water, no change in concentration, and this boundary condition is followed. It cannot be used everywhere, but that is what has been done quite often. And error function complementary is called 1 minus E r f y. So, this value will vary from 0 to 1, and 1 minus this error function y is complementary error function, and you can actually get error function is equals to 0, error function infinity is equals to 1. So, it varies from 0 to 1, therefore, 1 minus this is called complementary error function, and one can use this. So, for C 0 equals to 0, this equation can be written in this manner, that is initial chloride concentration is 0. One can write it in this manner, where x is any distance, d is the diffusion coefficient, and t is the time. replacing CDT is equals to, at the cover depth it is as threshold. So, this CXT I replace it by D, x equals to D, at x equals to D, and at time some time C is equals to TH, then I get CTH on this side is equals to CF, where this is equals to D. This is the, then this T is the service line, this T is the service line. Then when the chloride level at the reval level, at the D is the cover depth, at the reval level has reached threshold. And one can actually, the formula may be approximated by a parabolic function like this error function, it can be actually approximated by a parabolic function, and you can get service life like this, an expression for service life like this, right. But there are a lot of uncertainty in this one. For example, CTH, as we said, is varies. There are threshold values would depend upon cement type, steel type, etc., and it is not constant. It is not sure how you measure the diffusion coefficient. There is no way really systematic way to measure the diffusion coefficient. So, T0 is the initiation time, or TP depassivation time. This, and a lot of people use this calculation, but this is absolutely inaccurate. One can possibly use experience rather than using something which does not exactly represent the real life situation, not the exact boundary condition. Saturated concretes are rare, but people do use them. Unsaturated concrete is mostly unsaturated, and this flux, concentration dependent flux, is same as earlier we talked about. But the chloride can migrate with solution, because unsaturated solution can go in. So, chloride can not migrate, sorry, chloride can ingress. Migration is under electric field. So, ingresses it can go under the capillary suction, and that flux is much higher usually. So, in splash zone and foundation or many other places where concrete is unsaturated, one can use this. So, unsaturated concrete is the most important one, and equation for this is fairly complex. I will just take half a minute and conclude our discussion on this and continue to the next lecture on the same one. Now, you can see that this is the flux of chloride, D is the diffusion coefficient. So, this is under concentration gradient, this could be under activation, because reaction might be taking place, and if there is a external potential applied, the migration can be occurring. So, migration potential, activation potential, reaction, actually activity, reaction potential, and this is due to the suction, water suction, the capillary suction or solution flux. Now, this flux is much more than this flux, and this is the diffusion coefficient. So, if you are looking at the total flux, that should be sum of the solution flux plus the flux. This may not be there if there is no external field, you can neglect this, at least two fluxes one must consider. And one, since there is a total chloride and free chloride, one must look at the mass balance of the total chloride, and under such condition, one must take, the equation would turn out to be this flux change is equals to some chloride binding factor must be taken into account. So, equation would be much more complex than what actually we have done. Therefore, error function solution does not represent real situation in most of the cases in any manner, it does not. Chloride binding, this is the factor of chloride binding, total chloride to free chloride ratio. You must balance the total chloride and the flux, rate of change of flux which you have used earlier, it would be something like this. So, quickly we can look into cause of depassivation can be diagnosed from chloride concentration. If you have both chloride, some diagrams are available. For example, carbonation depth to cover depth 1, the risk is relatively low, but if it is more than 1, that is carbonation only, chloride is relatively less. Here both chloride and carbonation is less, but chloride is high, risk of corrosion is high. Here both carbonation and chloride is high, risk of corrosion is high, this is high. So, chloride risk is high, both carbonation and chloride is there, only carbonation, chloride is not there, and it has not reached to the cover depth, risk of corrosion is low. Otherwise, if it has crossed the cover depth, carbonation has crossed the cover depth, but chloride is low, moderate. This zone is moderate, where carbonation is less, but chloride has reached its threshold. Well, these are some guidelines available, but may not be very, it can be used in situ concrete. chloride diffusion coefficient, it has been seen that sulphate resistant cement gives you high chloride diffusion coefficient compared to slag or slag OPC combination or fly ash OPC combination. So, sulphate resisting cement is no good for chloride situation. Blended cements, however, controls the corrosion kinetics much better, that is well understood. They but with respect to carbonation, of course, we have already said that this may not be very good. I think we'll close down here and starts from like basically protection, same as some of the total chloride remain physically and chemically bound with cement, that is what we said. So, protection would be this already we have seen blended cement performs better. So, what we have seen is protection would mean impervious concrete C3A, higher C3A, but C3A would actually do well as far as chloride. Higher C3A improves chloride binding, but may not do sulphate very well, while slag cement is better for both sulphate as well as chloride. So, higher C3A improves chloride, right, and impervious surface concrete, lower water cement ratio, adequate cover depth, PPC etc. improves chloride. Threshold chloride depends on steel, blended cement performs better, and initiation period depends on steel type, ratio of acid soluble chloride to water soluble chloride is this, that is gamma values is something like this. So, if you have a crack, then chloride can penetrate and it can cause what is called pitting corrosion, that is what is shown here. So, with this we can actually summarize our discussion. We have looked into carbonation and chloride together, and as far as chloride is concerned, we said that the C3A it gives better binding, carbonation, impervious concrete and low water cement ratio is always better, and depassivation time we have looked into some of the models, and with this, thank you.